Hey everyone, welcome. Today, we're going to jump right into one of the biggest ideas in all of science, the flow of energy. We're going to break down what makes everything in our universe tick, what makes things move, change, and, well, work.
So here's what we've got on the agenda. First, we'll tackle the big question, what is energy anyway? From there, we'll look at all its different forms, follow its path from the sun all the way to us, and then get into the one rule you have to know about it. We'll also cover how we measure it, and then, of course, we'll do a quick recap of the must-know points. Okay, let's dive into our first section. What is energy? Seriously, getting this part down is super important because everything else we're going to talk about builds right on top of it. So let's start with the biggest question of all. What actually is energy? I mean, we throw that word around all the time, right? I've got no energy today, or whatever. But in physics, it means something very, very specific. So let's nail down that definition.
Okay, here it is, the textbook definition. Energy is the ability to do work. Now, work is just a physics term for when a force makes an object move. A much simpler way to think about it, energy is just the capacity to cause change. To make something happen. If something is moving or heating up or changing in any way, that's energy doing its thing.
So, energy basically comes in two main flavors. You've got kinetic energy, that's energy in motion. Think of a rolling ball, a moving car, anything that's actually moving has kinetic energy. Then you have potential energy. This is stored energy. It's energy that's just waiting to happen. A great example is a compressed spring. It's got all this potential to do work, and as soon as you let it go, that potential energy transforms into kinetic energy. All right, that brings us to section 2. So we've got kinetic and potential as the two main states of energy. But those states can show up in a bunch of different forms. Let's take a look at the whole energy family. So here are the big 6 you're going to see over and over. Mechanical, chemical, electrical, radiant, thermal, and nuclear. And yeah, they might seem totally unrelated at first glance, but you'll see that they're all just different faces of the same thing, different ways to get work done. Let's start with mechanical energy. This is probably the one that makes the most sense right away. It's the energy of things in motion, a car driving, an elevator going up. It's basically just the total of an object's kinetic and potential energy all mixed together in a system.
Then we've got chemical energy. This is a type of potential energy that's stored right in the bonds of molecules. Think about the food you eat. That's pure chemical energy. Your body breaks down those molecules to release the energy that lets you, walk and think. It's the same idea with gasoline in a car or wood in a fire. You're just breaking chemical bonds to release stored energy.
And then there's electrical energy. This one's all about moving electrons. The really important thing to remember here is that it's what we call a secondary source. That means you can't just go out and find a bucket of electricity in nature. We have to make it by converting another type of energy, like burning coal or using nuclear power to get those electrons flowing.
Okay, next up is radiant energy. This one is pretty cool because it travels in electromagnetic waves. Think of light from the sun, or even microwaves in your kitchen. What's wild is that it doesn't need anything to travel through. That sunlight you feel on your skin, it traveled all the way through the emptiness of space to get here.
Thermal energy is what we usually just call heat. And what is heat really? It's just the energy from tiny molecules and atoms inside something moving around, vibrating and jiggling. The faster they move, the hotter the object is. And there's a golden rule here. Heat always flows from a hotter thing to a colder thing. It's why your cup of coffee gets cold. All that thermal energy is just moving from the hot coffee into the cooler air in the room. And last but not least, we have the heavyweight champion, nuclear energy. This stuff is packed into the very center, the nucleus, of an atom. You can release it in 2 ways. Fusion, which is when you smash atoms together, that's what powers the sun, or fission, where you split them apart, which is how nuclear power plants work. It's incredibly powerful. Okay, so we've got all these different kinds of energy, but where does it all come from? In this next part, let's play detective and trace the energy on Earth back to its original source. So where does most of the energy on our planet originate? I'll give you a hint. It's that giant ball of fire in the sky. Yep, the sun. Its radiant energy is the engine that drives pretty much everything. Our weather, the oceans, and crucially, photosynthesis, which is the base of nearly all life. And get this, even fossil fuels like coal and oil are really just ancient sunlight stored by plants millions and millions of years ago. Kind of mind-blowing when you think about it. Now, even though the sun is the ultimate source, we humans have gotten really good at tapping into different energy reserves. Just take a look at this table. It shows how the U.S. energy sources changed between 1975 and 2000. You can see right away how things shifted, right? Coal and nuclear power went way up, while crude oil production actually went down.
And this chart here tells that same story, but visually. Look at how that slice for crude oil gets smaller, while the coal and nuclear slices get bigger. It's a great reminder that how we get our energy isn't set in stone. It changes all the time depending on things like new tech and what's happening in the world.
Okay, now we're getting to something huge. This is a fundamental rule of the universe, one that applies to every single bit of energy everywhere. Seriously, if you remember only one thing from this whole chapter, make it this.
It's called the law of conservation of energy. And it says this: energy cannot be created or destroyed. It can only be converted from one form to another. Think about that for a second. It means the total amount of energy in the universe is constant. It's always been here and it always will be. It just changes its costume, so to speak.
Let's look at a motorcycle to see how this works in the real world. A motorcycle doesn't just create energy out of thin air. It starts with chemical energy stored in the gasoline. The engine then does its magic and converts that chemical energy into two other forms: kinetic energy, to make the bike move, and thermal energy. That's the heat you feel. No energy was created or lost. It was just transformed.
All right, so to really talk about energy like a scientist, we've got to know the lingo. And that means understanding the units we use to measure it.
This chart is basically your cheat sheet. The standard unit of energy is the joule. But here's a super common point of confusion: the difference between energy and power. Power, which is measured in watts, is how fast you're using energy. And that kilowatt hour on your electric bill, that's actually a unit of energy, not power. It's measuring the total amount of energy you used over a whole month, for example.
Okay, we have covered a ton of stuff. So before we finish up, let's do a quick recap and hit the most important takeaways you'll need for your quizzes and presentations.
Let's boil it all down. If you can walk away with these 4 ideas, you're in great shape. First, energy is the ability to do work. Simple. Second, it's usually in one of 2 states: kinetic, which is motion, or potential, which is stored. Third, energy can change from one form to another, like chemical to thermal. And finally, number 4, the big one, the law of conservation of energy. Remember, you can't create it, you can't destroy it. And I want to leave you with one final question to chew on. We always talk about energy being lost to friction, right? Like the heat coming off that motorcycle engine. But we just learned that energy can't be destroyed. So where does that so-called lost energy actually go? Think about that as you move forward in your course. Thanks for tuning in.